Trustworthiness requires a commitment to rigor in both software production and its verification. No soft skill, rigor has a hard edge. In an environment of neglect and unmet need, the introduction of rigor would be a game changer, one that requires both cultural change and engineering know-how with pass-fail training certification. Software assurance only has meaning in the context of trustworthiness. That is, worthy of being trusted to fulfill the critical requirements needed for a particular software component, system, or system of systems. Software assurance demands two capabilities associated with trustworthiness: the capability to produce trustworthy software products and the capability to verify that software products are trustworthy. Each depends on engineering and technology rigorously applied. The kernel of the layered defense approach to software assurance is build security in and structured programming with its rigorous and provably correct use of 0 and 1 predicate prime programs, along with proper programs composed of multiple prime programs limited to single entry and single exit. The layered defense approach described here includes defense in depth, build security in, risk management calculation, and resilience processes, engineering, and tool automation, dependent on an elevated state of software engineering rigor and precision. There is much room for improvement in the software assurance methods and practices that assure such rigor. For the purposes of this Department of Defense ASD Research and Engineering RFI, the term software assurance, or SWA, means the level of confidence that software functions as intended and only as intended, and is free of vulnerabilities, either intentionally or unintentionally designed or inserted as part of the software throughout the life cycle. On July 31, 2007, the Software Assurance State-of-the-Art Report described the emerging activities, approaches, and technologies thought to be the foundation of the discipline of software security. While the report mentioned inspections, static analysis, function extraction for malicious code, common weakness enumeration, and standard of excellence product checklists, it did not include structured programming, cleanroom software engineering, or statistical testing. Build security in depends on the adoption of all of these methods. Also not mentioned in SOAR were technical debt and build security in, except for a reference to a portal name. Importantly, SOAR identified the need for security extensions to the CMMI, so far only discussed and not acted upon. Resilience was mentioned in the context of resistance to and tolerance of attack, fault tolerance, and system failure recovery, but not in the context of anticipating, avoiding, withstanding, mitigating, and recovering from the effects of adversity, whether natural or man-made, under all circumstances of use, including both systems and systems of systems. The current state of software assurance is dire and stems from a combination of neglect and unmet need. The future state of software assurance needs to feature smart and trusted methods and metrics, including software assurance risk calculation that is precise, accurate, timely, and complete. Some unmet need is due to lack of adoption, and some to lack of technology. Lack of adoption falls on both industry practitioners and government acquisition specialists. Neglect is on glaring display in the international practice of technical debt, spurred on by a misguided culture of acceptance. Furthermore, the shortfall in STEM workforce yields a persistent level of unintentional neglect based on ignorance. Beyond software assurance adoption, the focus areas most in need of attention are build security in, resiliency, advanced technology, and renovation of the CMMI to address software assurance. The layered defense approach recommended here includes defense in depth, build security in, risk management calculation, and resilience. Defense in depth is composed of encryption, identity management, access control, authorization management, accountability management, incident management, configuration management, and security assurance operations. Build security in is composed of structured programming with emphasis on correctness, cleanroom software engineering, and statistical testing. Static analysis tool use, function extraction tool use, and common weakness and known vulnerability evaluation. Risk management calculation includes goal identification and actually calculating risks based on systematically distinguishing factors, sources of risk, and problems using levels of confidence. Resiliency prerequisites are defense in depth, business continuity, and survivability. And features of resiliency include coordinated recovery time objectives, digital situation awareness, distributed supervisory control, selective availability, operation sensing and monitoring, information and data recovery, and interoperability of data and information exchange. These layered defense tactics of the preferred governance model are assessed in the table that follows in subsequent slides. In terms of software assurance practice and technology, distinguished by known practice, underutilized technology, and advanced technology needed. A framework of cyber tactics, including anticipation, detection, attribution, and countermeasures, is needed to reason about tools, tiers, and threat categories. Cause and effect chain elements spanning goals, weaknesses, attributes of building security in, attack outcomes, bad actors, and consequences must be identified and traced for selected cyber tactics. Consequences must be traced for selected goals and attack outcomes. In the spirit of continuous improvement and consistent with the erratic and rapid pace of both technology and threat emergence, all methods and means, including tools, need to be assessed, evaluated on a continuous basis. Refreshment and update is not so much periodic. Instead, refreshment is on demand in accordance with the check everything every time principle. The practice of technical debt fosters permissible and persistent neglect and needs to be discontinued and eliminated. While the CMMI provides an excellent platform for achieving widespread adoption for software process maturity, it is incomplete with respect to software assurance and cybersecurity process. The importance of underutilized technology lies in the potential of the CMMI and its widespread infrastructure of usage to serve as the platform for software assurance adoption and dissemination. With respect to defense in depth, encryption, authorization management, and security assurance operations are underutilized practices. In addition, three-factor authentication based on what you are, what you have, and what you know is an underutilized technology. Finally, trusted encryption advances are needed. The table also highlights the advanced technology needed, and here defense in depth awaits trusted encryption advances. With respect to build security in, there are numerous underutilized practices, including structured programming with insufficient emphasis on correctness and proof of correctness, and inspections with well-defined standard of excellence spanning completeness, correctness, style, rules of construction, and multiple views. Cleanroom software engineering with its underutilized practice and statistical testing and its underutilized technology. Function extraction and its underutilized practice and technology and its need for advanced technology. And underutilized practice of common weaknesses and known vulnerabilities and the need for additional advanced technology. With respect to structured programming, specifically, the rigorous and provably correct use of 0 and 1 predicate prime programs, along with proper programs composed of multiple prime programs limited to single entry and single exit, is the kernel of trustworthy software assurance. The table highlights the advanced technology needed. Static analysis needs commonality and interoperable tool vendor results, post-processing advances, to disambiguate multi-vendor results and decimate the number of false positives. Function extraction needs to be able to process large programs and systems, such as those found in legacy software systems, COTS, reuse libraries, and commercial software releases. In addition, function extraction needs to be able to process source code from a wide range of languages and object code from various instruction set architectures. Common weaknesses and known vulnerabilities need to be integrated with static analysis tool automation. With respect to risk management calculation, while goal identification is commonplace, actually calculating risks based on systematically distinguishing factors, sources of risk, and problems using levels of confidence is an underutilized practice. Beyond that, determining the level of confidence in assigning a failed state to a factor is assisted by evidence-based assurance assessment questions. The table highlights the advanced technology needed, and here risk management calculation needs to apply cognitive systems, that is, IBM Watson, with its emphasis on levels of confidence useful in calculating risk. With respect to resilience, coordinated recovery time objectives, digital situation awareness, selective availability, and data and information exchange represent underutilized practices and features. The table highlights the advanced technology needed, and here, resilience needs to apply cognitive systems, that is, IBM Watson, with its potential for anticipation, avoidance, and digital situation awareness. Cooperation in promoting software assurance adoption is expected from the industry and required by the government and the acquisition community. DoD, DHS, and NIST are the principal government agencies involved. IBM, Lockheed Martin, General Dynamics, Raytheon, and Northrop Grumman are key participants in the defense industrial base. Carnegie Mellon University, with its Software Engineering Institute and CMMI Institute, University of Maryland Robert H. Smith School of Business, and MITRE are key knowledge resources in software, software assurance, cybersecurity, and supply chain risk management assurance domains. Also, certain technical publications are excellent vehicles for reaching diverse software assurance audiences. These include Crosstalk, the Journal of Defense Software Engineering, the Defense AT&L Magazine, and IEEE Reliability Society publications. Means of operating would be direct with industry through the acquisition community, assisted by a newly formed Center for National Software Assurance, CNSA, in the form of a 501c3 nonprofit organization or a university center of excellence, such as the University of Maryland Robert H. Smith School of Business Supply Chain Management Center, or the Carnegie Mellon University CMMI Institute. The CNSA would attempt to understand the past and current directions of the software profession in order to anticipate next-generation software engineering and to guide its impact towards consequential outcomes in the security and competitiveness of the nation's critical industries. Currently, the state of software and software assurance are dire. The CNSA would be organized to drive the software assurance initiative and would be established to elevate software assurance to the national agenda across industry, government, and academia in addressing issues of national importance in security and competitiveness. The CNSA would initiate and sustain a cross-cutting software assurance steering group composed of industry, government, academia, and the acquisition community. The steering group would focus on promoting organizational commitment to software assurance excellence, along with the certification training and assessment metrics needed to advance it. The line of sight for a target organization adopting software assurance is guided by a 5-level maturity value map, including defense in depth, build security in, risk management calculation, and resilience. Software assurance maturity seeks some of the same consequential outcomes as traditional organizational maturity, such as more efficiency, more predictability, less risk, and less chaos. Accordingly, efforts would be directed at incorporating software assurance and cybersecurity into the CMMI in order to utilize its existing effective dissemination and adoption infrastructure. While software assurance certification programs and university degree programs may successfully impact and meet the developmental needs of individuals, the organizational capability and its systematic appraisal and assessment would be tied to a software assurance-enabled CMMI. Level 2. Defense in depth, including standards for existing methods and practice for assuring software security focus on protection from vulnerabilities and threats through security in depth. Protective measures include encryption, identity management, access control, authorization management, accountability management, incident management, configuration management, and security assurance operations. Level 3. Build security in, including standards for existing methods and practice for trustworthiness, focus on building security in by constructing software components, systems, and systems of systems to an engineered standard of excellence based on completeness, correctness, and rules of construction. Beginning with discontinuing the practice of technical debt, build security in practices include structured programming with an emphasis on correctness, cleanroom software engineering and statistical testing, software inspections process with well-defined standard of excellence, the application of static analysis tools, the use of common weaknesses and known vulnerabilities, and the application of function extraction. Level 4. Risk management calculation, including standards for existing methods and practice for calculating software assurance uncertainty, focus on factors, sources of risk, and problems evaluated for each goal. Account of factors that might serve as sources of problems in goal achievement, and account of factors that represent objectives that are in a failed state. Determining the level of confidence in assigning a failed state is assisted by evidence-based assurance assessment questions. For each goal, the calculated risk is the number of problems divided by factors evaluated, expressed as a percent. Level 5. Resilience of systems and supply chains, including standards for existing methods and practice for assuring resiliency under stress. Focus on anticipating, avoiding, withstanding, mitigating, and recovering from the effects of adversity, whether natural or man-made, under all circumstances of use. Features of resiliency engineering include coordinated recovery time objectives, digital situation awareness, distributed supervisory control, selective availability, operation sensing and monitoring, information and data recovery, and interoperability of data and information exchange. The Center for National Software Studies, CNSS, operated as a nonprofit 501c3 for a decade. The CNSS model would be ideal for a Center for National Software Assurance, CNSA, including the structure for mission, goals and objectives, operational concept, and all officer and board governance matters. Governance model costs for operating a Center for National Software Assurance, CNSA, are projected over a 5-year planning horizon that support the time frame for software assurance adoption as follows. Year 1, $2 million. Year 2, $3 million. Year 3 to 5, $4 million, totaling $20 million. Expected funding sources would include both government and industry. Cost of adoption is borne by the industry and the government programs they participate in. Improved software assurance is expected to deliver reduced costs in programs going forward. Time frame is tied to the rate of software assurance adoption for committed organizations, including immediate acceptance at level 1, with explicit commitment expected in 6 months. Near-term usage at level 2, with defense in-depth expected in 6 to 9 months. Mid-term usage at level 3, with build security in expected in 12 to 24 months. Mid-term usage at level 4, with risk management calculation expected in 9 to 18 months. And long-term usage at level 5 with resilience of systems and supply chains expected in 24 to 48 months. The best way to get willing participation is to expect it. To accomplish the game-changing cultural transformation in trustworthiness and rigor in both software production and its verification, the best approach is to ask those who need to follow the improved standards to participate in the process of both developing and applying software assurance standards. The expectation of willing participation is based on the premise that dramatic software assurance improvement is an imperative, and that industry firms are essential to accomplishing the improvement. The Center for National Software Assurance, CNSA, would engage the defense industrial base, defense contractors, and the defense acquisition community in its initial formation, including the establishment and refinement of its program of operation, the recruitment and sourcing of staff, and the identification of issues of national importance. Attention and care would be taken in team building, in forming a software assurance steering group, and the effective working groups needed to address software assurance issues of national concern. The prerequisite for participation would be an explicit commitment to rigor in both software production and its verification, and to the cultural change and staff development needed to realize it. Improved software assurance would reduce software defects and cybersecurity incidents, and with it, reductions in cost, liability, and operational risk and impact. Defect insertion and detection rates, when placed under control, provide a useful measurement in reducing operational risk. Return on investment provides a useful means to regulate the investment needed to reduce liability risk. The build security in software inspections process using the well-defined standard of excellence delivers a return on investment of 4 to 1 measured over a decade of use. Security return on investment has been difficult to calculate successfully. In the return of actual data on the number of incidents, organizations are often forced to make estimates. These estimates can be used to calculate security return on investment. While the impact of an individual incident can be difficult to assess, it is clear that cost avoidance stemming from avoiding lost opportunity costs, cleanup costs, and recovery costs can be substantial. A stepped-up expectation for excellence in software assurance practice in DoD acquisitions would incentivize industry. As for protections, it is essential that risk management tactics be embedded in software assurance practices, guidelines, and standards through the identification, mitigation, transfer, or acceptance of factors, sources of risk, and problems that may impede the achievement of software assurance goals and objectives. Furthermore, embedding software assurance in the CMMI would incentivize both industry and government to advance the maturity of software assurance. Finally, public policy tactics that stimulate innovation and technology and that eliminate shortfall in its deployment include: number one, market-driven tactics are centered around industry standards activities, voluntary compliance, and public-private collaboration for information sharing. Number two, targeted investment and funding can be used to stimulate research in critical areas. Number three, tax policy, such as the Research and Engineering Tax Credit, can be powerful, but it is difficult to get all stakeholders on the same page. These include the creators of technology, the users of technology, the legislative community, the legal profession, and the judicial arm. Trustworthiness requires a commitment to rigor in both software production and its verification. No soft skill. Rigor has a hard edge. In an environment of neglect and unmet need, the introduction of rigor would be a game changer, one that requires both cultural change and engineering know-how with pass-fail training certification. Software assurance demands two capabilities associated with trustworthiness: the capability to produce trustworthy software products and the capability to verify that software products are trustworthy. Each depends on engineering technology rigorously applied. The table evaluates the build security and methods discussed in terms of degree of rigor, suggesting a ranking of rigor as first tool automation, then engineering, and finally process. Not just tools in a toolbox, the build security and methods represent the core competencies that serve as the center point for trustworthiness and rigor. A straightforward assessment of enterprise commitment to these software assurance core competencies can be found in the following questions. Number one, to what extent has the organization adopted structured programming and explicitly applied it in practice? Number two, to what extent has the organization adopted correctness by construction and expertly applied it in practice? Number three, to what extent has the organization adopted clean room software engineering and expertly applied it in practice? To what extent has the organization adopted the evaluation of common weaknesses and known vulnerabilities and expertly applied it in practice? Number five, to what extent has the organization adopted a defined standard of excellence and expertly applied it in practice? Number six, to what extent has the organization adopted static analysis and expertly applied it in practice? Number seven, To what extent has the organization applied statistical testing and expertly applied it in practice? Number 8. To what extent has the organization adopted function extraction and expertly applied it in practice? The layered defense approach recommended here includes the defense in depth, build security in, risk management calculation, and resilience engineering and processes dependent on an elevated state of software engineering rigor. There is much room for improvement in the rigor of software assurance methods and practices. Software assurance is impeded by the acceptance of technical debt, a practice that breeds neglect and should be discontinued. Advancing software assurance adoption would be stimulated by renovating the CMMI to include software assurance and cybersecurity process capabilities. Strengthening defense in depth, encryption, authorization management, and security assurance operations practices is needed. Build security in, emphasis on correctness proofs, and the defined standard of excellence for completeness, correctness, style, rules of construction, and multiple views is the required foundation for the increased rigor being sought. The full utilization of statistical testing, function extraction, and static analysis automation would verify and calibrate the improvement in rigor in a cost-effective and schedule-efficient manner, enabling the next generation software engineering goal of doing more with less fast. Much needs to be done on resilience, including the widespread implementation of resiliency functions and features. The CNSA would be organized to drive the Software Assurance Initiative and would be established to elevate software assurance to the national agenda across industry, government, and academia in addressing issues of national importance in security and competitiveness. With genuine attention and care taken in team building, in forming a software assurance steering group, its initial focus would include the establishment of its program of operation, the recruitment and sourcing of staff, and the identification of issues of national importance, and the formation of working groups needed to address critical software assurance issues. A governance model would ensure the DoD focus needed to deliver consequential outcomes in the technical capabilities that promise to reduce the cost, acquisition time, and risk of major defense acquisition programs. Here is my contact information. I would be happy to receive questions and have discussions with people on this important subject.